Hello, good to see you all. Very pleased to introduce Hung Chu from University of Illinois Urbana-Champaign. Hung is a graduate student there, and he is today speaking on relaxation of optimality for the thresholding greedy algorithms.
Thank you very much for the introduction, and thank you everyone for showing up. It is great to be here and to deliver this talk. So just let me get started. So I will talk about the thresholding greedy algorithm and how we might relax the optimality for the algorithm. So here I have an outline of the talk. You see in the first two sections, we will do a quick literature review. We will discuss the TGA and related properties. We also look at almost greedy and greedy basis. In section 3, we discuss the problem of relaxing optimality just briefly. And section 4 and 5, we will look at in details some more results, some recent results regarding F-greedy type basis. And the last section, section 5, is about the equivalence between F-greedy and F-almost greedy, which is a bit surprising because in general, this is not true for all function f, but it is true if f grows slow enough. Okay, so that is the outline, and here's the first section, the thresholding greedy algorithm, or the TGA. Here's the setting. Let X be any infinite dimensional separable Banach space over the field F. This field F can be the real or the complex numbers. And XR is the dual of X. Now to define a basis. A basis is any countable collection of vectors En in the space such that three properties are satisfied. The first one is that if you look at the closure of the span of the En, then you have the whole space. The second property is that if you look at there exists a collection of functionals En star in the dual such that En star En is a conical delta function Nm. Or the collection En star is sometimes called the bi-orthogonal functionals corresponding to our basis, our collection En. The last property is that the norm of En and En star are bounded away from 0 or infinity. This is what we call semi-normalization. So if you have a collection that have these three properties, then we say that we have a basis. Okay? Now, in our setting, we do not require the basis to be Schauer or Markushevich. In fact, in order to be Markushevich, you need the basis to be total, but here we do not need the totality for our basis. The last remark I want to make is that this definition of basis is order-free. So if you have a collection, if you have a basis, and then no matter how you reorder the basis, it is still a basis. So this definition is order-free. So let me discuss some approximation method. Well, one main goal of the approximation theory is to approximate a vector x by some finite linear combination of the basis. And maybe the most convenient way is to just look at the partial sums of I'm going to say the first n terms or a linear combination of the first n terms in the basis, an, en, and n runs from 1 to m, right? But there are some drawbacks to this approximation method. The first one is that you cannot measure with high level of accuracy. The second one is that this method is dependent on how you order the basis, because you are talking about the first n terms in your approximation, right? So this notion is somewhat in contrast to our definition of a basis, because our basis is order free. But here, if you use this approximation method, you actually depends on the order of the basis. So in order to remedy this problem, in 1999, Koyagan and Charikov introduced the thresholding greedy algorithm. But before we discuss the algorithm, we need to define greedy sets and greedy sums. So let n to the power of less than infinity be the set of all finite subsets of n. Then for every vector x, you can associate x with a sequence of scalars, and this sequence is simply by applying the functionals en star to x, and you have a sequence of real or complex scalars. For every finite set A, TAX is the projection of x onto A, which is the summation of En star x En for n in A. This is simply a projection, but A here has to be finite in order for this summation to be qualified. In general, lambda, a finite set lambda is a greedy set of x of order m if the size of lambda is m and the minimum of the coefficient in lambda is at least the maximum of the coefficient that is not in lambda. So this is a very natural definition of greedy sets. Right? Then the corresponding greedy sum is simply the projection of x onto lambda. Right? So greedy sum is the projection of x onto its greedy set. And finally, let GXM be the set of all greedy sets of x of order n. Okay, so that is the setup before we can discuss the TGA. And here again, in 1999, Koyagan and Chanukov introduced the TGA. You can think of it as a map from x, from any vector x to a sequence of its greedy sums, and the size of the greedy sums increases. So here you see lambda 1 is the greedy set of size 1, lambda 2 is the greedy set of size 2, and this keeps increasing from n equals 1 to infinity. And the nice thing about this algorithm is that it is order free, because if you have the largest coefficient in some order, then you also have the same largest coefficient in some other order, in any other order. So that is a TGA. And now you have an algorithm. You want to know how well it performs, how well an approximation that the TGA can offer. So here we want to, okay, so the first question is like, does the sequence converge to X or not? This is not necessary, and we also have a name for such a basis. This is also a definition due to Koyagan and Charikov. They say that the basis is quasi-greedy if the sequence of greedy sums converge to X for all X and for all greedy sums lambda m, because lambda m might not be in big. So that's why I have to have the quantifier for all lambda m in GXM. So that is the definition of quasi-greedy. And when you look at this condition of convergence, you might think about like, okay, do we have boundedness? And can we characterize this convergence by boundedness of the projection onto greedy sums? And the answer is yes, but you need to do it under some extra condition. So a basis is shown if you have, for any set A, the span of En for n in A, taking the closure, is equal to the set of all vectors whose support are in A. So if you have this condition for your basis, I would like to say that's show the basis as shown. And if you have this condition, then the convergence in the definition of quasi-greedy is the same as the projection onto p lambda x onto lambda is bounded by x. Right? So this convergence is equivalent to this boundedness, assuming that our basis is shown, and this boundedness means that for all x and for all greedy set lambda, if you project x onto lambda, then the new vector, the projection is bounded by x. Okay, so this is the last concept that we need in this section. This is unconditionality. A basis is unconditional if for any set A and for any x, if you project x onto A, then the projection is always bounded by the original vector. So you already see that this definition of unconditionality means that an unconditional basis is quasi-greedy, right? Because for quasi-greedy basis, you only have this bound if A is a greedy set of X. But here you have this bound for all set A. So of course, unconditional implies quasi-greedy. Right? So here are some examples of bases that are conditional or unconditional. Again, if a basis is not unconditional, then we say it's conditional. The first example is the Haar system in LP 0 on the interval 0, 1, and it is unconditional for all p greater than 1. But for p equals 1, the Haar system is not quasi-greedy, not to mention unconditional. The trig system LP on the unit circle is unconditional if and only if p is equal to 2, but for any other values of p, the trig system is not quasi-greedy. Okay, so before I move on to the next section, this is again, I just want to emphasize that quasi-greedy is the consequence of unconditional. But I'm sorry, anyone has a question? Okay. So, however, quasi-greedy does not imply unconditional. And here is an example, again, also due to Kollegen and Chalokov from 1999. And this example, if you look at the closure of the completion of C00 with respect to this norm, then the canonical basis is quasi-greedy but conditional. So, okay, so that's the end of the first section. We have seen the TGA, we have seen quasi-greedy and unconditional, and some related concepts like greedy sets and greedy sum. The next section will be about different greedy type bases. Here we have almost greedy or greedy bases, and how we and I also discuss how we characterize them in some of the classical results. Okay, here is the definition of a basis being greedy. So a basis is said to be greedy if if you look at if it satisfies this inequality, and if you look at the left side of this inequality here, this is the distance between x and a greedy sum lambda, right? But on the right side, this is the distance between x and any linear combination of m terms in the basis, right? So you see the set A here have size bounded by m, and then A can be any set as long as it is bounded by the size is at most m, and then you take the linear combination of these En for n in A. So this inequality tells us that in order for a basis to be greedy, then the greedy sum essentially gives you the best m-term approximation that you can possibly have. So this condition, I would say, is relatively hard to check directly for some bases. So the question is there a nice way to characterize such a basis. And this will lead us to a result by Quaternion and Chalakov in 1999. But before that, we need to define a basis being democratic. So here, if you give me any finite set A, then 1A is the indicator function defined to be the summation of En for n in A. A basis is said to be democratic if 1A is bounded by 1B, given that the sign of A is at most the sign of B. So we are ready to state the result by Quaternion and Chalakov. A basis is greedy if and only if it is unconditional and democratic. So now you see the two properties on the right side are relatively easier to check than being greedy. So this is a very nice and very classical characterization of greedy basis. Besides greedy basis, we also have almost greedy basis, and it was introduced in 2003 by Diogoz, Carlton, Kazarova, and Chalakov. So a basis is greedy if it satisfies almost the same condition as greedy, but on the right-hand side, you do not have any linear combination of vectors in the basis. Here you only have projection. It turns out that this introduction of almost greedy has a lot of application that I can show you later. But basically, you can see that this condition is already weaker than being greedy, and that's why the name is almost greedy. So can we characterize almost greedy basis? And the answer is yes. It is in the same paper by DKKT, they show that a basis is almost greedy if and only if it is quasi-greedy and democratic. So if you compare this with the result by Quaternion and Chalakov, then here they replace unconditionality by quasi-greedy. So that's why almost greedy is weaker, right, than being greedy. Okay, so I just restate what I mentioned. Greedy implies almost greedy, but the reverse does not hold. Here I want to squeeze in a recent result in my joint work with Barasetagi and Berna. We show that instead of projecting on all set A, like in this case for all set A, we can just project on interval. So here I is an interval, and you look at the difference x minus pix, and that would be strong enough to give you almost greedy. Right? Even though you look at this condition and you know that this condition is weaker at the first glance compared to this condition, because the right side here is bigger than the right side here. But it turns out that this condition is the same as being almost greedy. Another surprising feature of this theorem is that when you think about the notion of being almost greedy, it is order independent or order free, meaning that if you have an almost greedy basis, then no matter how you permute the basis, the permutation is still almost greedy. However, if you look at this condition right here, you are talking about intervals. And of course, it is order dependent, right? Because whenever you talk about some consecutive elements, then you are talking about some ordering here. So that is surprising that this condition is order dependent, but it can characterize almost greedy basis. Okay, so we want to discuss how rare greedy bases are, and this was some results due to Dilworth, Freeman, Odell, and Schumpeter, and also by Chapman in 2011 and 2014, respectively. They show that a bunch of classical spaces do not have a greedy basis. So in some sense, greedy bases are not very common compared to almost greedy. So here is here's a slide about existence of almost greedy basis. And in a paper by Diogo, Carlton, and Kazarova in 2003, they show that if X contains a complemented copy of LP, then X has infinitely many inequivalent almost greedy bases. So a bunch of spaces that I mentioned in the previous slide will have almost greedy bases, even though they do not have greedy bases. And that's why we claim that almost greedy bases are much more common than greedy bases. Okay. Now, I want to end this section with a claim that might be surprising as well, which that is almost greedy bases, even though they are much more common than greedy bases, almost greedy bases are not far away from being greedy. And you could see this, you should see why this is true in the next section. So in this section, we will talk about how we might relax the optimality of the TGA. So this is another result in the paper by DKKT in 2003. They show that being almost greedy is the same as satisfying this condition. So what is this condition? This condition is very similar to the condition of being greedy, right? The only change that they make is that they restrict the size of A to to M over lambda for some lambda greater than 1. So by making that small change in the size of A, I mean they reduce it linearly, but it brings us down from being greedy to being almost greedy. So this is a very surprising equivalence that they prove in the paper. So we are curious and we want to know, can we do the same thing for almost greedy basis? Can we resize the approximant on the right side in the condition for almost greedy basis? And it turned out that we do not have anything new if we restrict the size of A in the projection onto A down to M over lambda, then we still have the definition of almost greedy basis. So this reduction only works if we reduce in the definition of greedy, but in the definition of almost greedy, it's a bit of a disappointment that we do not have a new kind of basis. However, this theorem still has some value that I will show you later. It will be used in one of our proof later. So let me do a quick summary. We look at almost greedy basis, and almost greedy basis is basically a comparison in terms of efficiency between greedy sums and projective approximants. Not linear combination, only projective approximants. And if greedy sums have size m and projective approximants have size m over lambda, then we recover the definition of being almost greedy. So maybe the right question to ask is, what if we shrink the projective approximants down further, like log m or root m instead of m over lambda? Then do we have something of a new type of greedy basis or not? And in order to do so, we need to define a collection F, and this is a collection of all the continuous differentiable increasing concave functions on the positive, and it satisfies a bunch of equalities and inequalities here. Again, I believe that several of these conditions can be relaxed a bit, but I choose to put them this way for our argument to be concise and also to avoid some technicalities in the details. And let F denote all such functions. This collection F is closed under composition. Right? So if you have two functions, you compose them, then the composition is still in F. And I also drew a bunch of of these functions here for you to see. Basically, before 1, you can go over the 45-degree line, but after 1, then you are lower than the 45-degree line. Okay. Okay. So that is a collection that we will use in our definition of f greedy and f almost greedy. Okay. So the f here is taken from the collection f. The only modification that we have here is that we restrict our set A to fm instead of m. So in the classical definitions, we have m, but now we only allow A to go up to fm. Okay. If f is the identity, then f greedy is the same as greedy. If f is linear, like x over lambda, then f almost greedy is almost greedy. So what can we do with this? Like, what are some motivation examples that might motivate our study of these properties? And here they are. So let me mention a few examples. The first one is the LP-LQ spaces. This space does not have a greedy basis, but if we frame the basis in our setting, then we can say that it has an XP over Q greedy basis. The multivariate class system HPD, here you need to have D greater than 1 and P is not 2, is not almost greedy, but it is x1 minus epsilon greedy for any epsilon. So even though the system here is not almost greedy, it is very close to being greedy. The last space I want to mention was constructed by Berner, Dearworth, Kazarova, Olberg, and Wallis in 2019. They construct a basis that is not democratic, right? So if it's not democratic, then it is not almost greedy. But it turns out that I'm sorry, I should say that they construct this basis in order I mean, this is one of the first examples of a basis that is not almost greedy, but partially greedy. We do not discuss partially greedy here, but I just want to say that this basis was constructed for some purpose, and it turns out that even though the basis is not almost greedy, it is square root of x greedy. Okay, so these are some motivation examples to motivate our research on these f greedy type basis. So let me move to the next section. Now we have some new notion of f greedy type basis. The question is, when can we characterize them in the same sense as some classical results from the 2000s or the 1999? The answer is yes, but we need to introduce some new notion. And the first one is F disjoint democratic. Now, we need two extra conditions here. The first one is that the psi of A is bounded by the psi of FB. Previously, for democratic, you only have A is bounded by B, but now you have the F function, so it's bounded by FB. And A and B are disjoint. Okay. The second one is an extension, or I would say a restricted version of unconditionality. Here you have the projection onto A is bounded by X, given that A contains a greedy set of X of size at least A minus FA. So you cannot do that for any set A, but you can do that for set A that satisfy. I mean, the bound does not apply for all set A, but it applies for set A that contains a greedy set of size at least A minus FA. And if you are observant, if you see that F is an identity, then this difference is 0. And if the difference is 0, then F of unconditional is the same as conditional, because you do not force any extra condition on the set A at all. Okay, so these are the setups, and let me state some of my recent results. The first two results here are characterizations of F greedy and F almost greedy basis in the same spirit as what you have seen in the classical result. But now we extend them to the case of F functions, of function F. The third result is surprising because now you have F greedy is actually the same as F almost greedy for all non-identity F. This result says that it doesn't matter whether you have projection or you have linear combination in your approximation. They are equivalent. The fourth result says that if G is bounded by F, then F almost greedy implies G almost greedy. The last result is that if the ratio of G over F is going to 0, then there exists an unconditional basis that is G greedy, but is not F almost greedy. So the reason why I highlight this in red is that I want to go into them into a bit more detail. And especially I will devote a section to give you a sketch of the proof of this result here, okay, of number 3. But before we end this section, as I mentioned earlier, let us talk about this theorem first. This theorem is you can if you have G over F is going to 0, then you have an unconditional basis that is G greedy, but it's not F almost greedy. And here is a construction. Here is a collection A, right? It consists of all finite sets, non-empty, that satisfy this inequality. So all the singletons are in A. And you let Xg be the completion of C00 under this norm. And you can see that the basis is 1 unconditional. Or you can also think of this as a modification of the trial space. Now, we will show that this basis is not F almost greedy. I will not show G greedy because it requires a bit more argument, but we can show that it is not F almost greedy quickly. In order to show that it is not F almost greedy, but you know that it's unconditional. So you want to show that it is not F disjoint democratic. Right? Okay, it is a definition. So some simple calculation give us this bound. If you define the vector 1an to be this vector n1s at the beginning, then the norm is bounded by gn over g1. This is not very hard to see. This follows directly from this inequality right here. If you have the vector 1bn and the set bn here is pushed far away to the right, so this vector contains fn1. So this is much less than n. Fn is smaller than n. But if you push it far away enough to the right, then it is equal to Fn. So you see that the ratio of 1bn over 1an is going to infinity because g is equal to small o f. Okay. So you have two sets, two disjoint sets satisfying the condition of disjoint democracy, but the ratio is not bounded. And so we conclude that the canonical basis is not F democratic. So it is not F almost greedy. I hope that this gives you a flavor of how we reject F almost greedy. However, we can show that it is G disjoint democracy. So combined with unconditionality, we can claim that it is G greedy, even though it is not F almost greedy. Okay. Before we move on to the next one section, let me talk about the multivariate system here. unit d is greater than 1. Okay? And I force d to be greater than 2. It doesn't matter. You can do the case p smaller than 2 exactly the same, using exactly the same argument. So let's talk about the hard system HPD for in the space LP with the interval 0, 1 to the d. And I choose epsilon greater than 0. Our goal is to show that the system HPD is x1 minus epsilon greedy. So how do we show that? Well, we know that it's unconditional. This is some well-known fact that was proved a long time ago that is unconditional. So the goal is just to show that it is x to the 1 minus epsilon disjoint democratic. And we will use a very nice proposition by Kirkiahedron, Pilkat, and Choyokov from 2006. So this theorem says that the norm of the indicator function at A is bounded below by m to the 1 over p, but bounded above by m to the 1 over p multiplied by some power of the log function. So the hard system is not democratic because the growth rate of the indicator functions are different depending how you choose hn. But the difference is not much, right? The difference is only log n. So that's I think now you see why we need the epsilon here, right? Because x to the 1 minus epsilon will take care of the log function here. So yes, so now we will show you a more rigorous argument. Okay, so we want to show x1 minus epsilon disjoint democratic, and we just pick two finite sets, A and B, to the 1 minus epsilon. Okay. Now we choose n to be sufficiently large such that after x go above n, then this function will dominate the log function. Okay, so here I assume that A is at least n, because for the case that A is at most n, then we can have some very trivial bounds. So we do not need to care much about that case. If A is greater than n, then we have, okay, so the first inequality here is using this inequality, right? We just replace n by the size of A. The next inequality is just a replacement of A by B, because the size of B is greater than the size of A. This inequality here, I'm using the way that n is chosen and the fact that A is at least n. Okay. And here you just have an equality, and the last inequality is coming from the lower bound for Hn. So you see that we go from 1a to 1b, and it is bounded. 1a is bounded by 1b. So that's why our space is x to the 1 minus epsilon greedy. Okay, so I want to devote the last section of my talk to, I could say, a very surprising equivalence between f greedy and f almost greedy for all non-identity f. Okay. So the first question is, why this is believable? Like without any proof, I mean, I should not say without any proof, without writing out all the details, why we can expect such an equivalence. And we can look at the extreme cases of function in f and see how they behave, right? If the extreme cases satisfy this equivalence, then we expect anything in between also satisfy this equivalence. So the two extreme cases would be bounded function and function that grow linearly. And here I let lambda greater than 1, right? Because we do not include the case when f is an identity. We only care about lambda greater than 1. For bounded function, you can easily prove that they are the same because f greedy and f almost greedy are equivalent and are the same as quasi greedy for bounded function f. For functions that grow linearly, then we need to recall some results that we discussed earlier. So let's say fx is x over lambda, then by a result of dkkt that I mentioned earlier, then x over lambda greedy is the same as almost greedy. But by a result that I also obtained recently, x over lambda almost greedy is the same as almost greedy. So from the equivalence, you can show that x over lambda greedy is x over lambda almost greedy. So now, for the two extreme cases, we expect the equivalence. We have the equivalence, so we expect the equivalence for all function f between these two extreme cases. So that's why I say, okay, quasi is believable. But let's quickly go over the detail. And here I only go over some proofs, the proof sketch. But we need two important results by Gutasik and DKKT. So the first result says that if you give me the indicator function at A, then no matter how I choose the scalar epsilon n, as long as epsilon n is equal to 1, then the norm is always bounded. The norm doesn't change much, right? The norm is bounded by some C1 and C2. The second result by Gutasik and DKK, they show that if you give me any vector x, assuming that the basis is quasi-greedy, you give me any vector x and any greedy set A of x. The indicator function at A, 1A, with the sign En star x, the norm of that vector multiplied by the minimum coefficient in the greedy set is bounded by the vector x. So this is called the TQG, or the truncation quasi-greedy property. For your information, the TQG right here implies UCC, and of course, TQG is a consequence of quasi-greedy. So assume that we have this result. I mean, we have the result, but we do not prove them in our slides. Let us show that f almost greedy implies f greedy, because the other implication is obvious. So we only do this implication. And we also assume that fx over x is going to 0, because if it's not going to 0, then it grows at least linearly. And we already show that when it grows linearly, we have the equivalence. So we assume that fx over x is 0, going to 0. Okay, so we also need to assume that we have the characterizations of f greedy and f almost greedy that I showed you earlier. Okay. Now we have all the tools that we need. If we assume these results, what we want to show is that quasi-greedy plus f disjoint democratic implies f unconditional. Right? Using this result combined with this, we will have the equivalence. Again, f unconditional means that the projection on any set A of x is bounded by x, given that A contains a greedy set of size at least A minus FA. So here's the proof. Assume quasi-greedy and f disjoint democratic. You fix a vector x in x and you choose a set A such that A can be written as a disjoint union of E and F. Here, E is a greedy set of size at least A minus FA, and F can be anything. We want to bound PAX by X. So a very quick result of a very quick consequence of being quasi-greedy, PEX is bounded by X because E is a greedy set and our basis is quasi-greedy. So this is taken for granted. So if we can bound PFX by X, then by the triangle inequality, we can bound PAX by X as well, right? So the goal is to bound PFX by X. After that, we have the triangle inequality, and we can bound PAX by X. So how do we bound PFX by X? Well, we just let alpha be the minimum of the coefficient in the greedy set E, and let beta be the maximum in the set F. Clearly, beta is bounded by alpha because our set E is the greedy set, so the coefficient must be larger than anything else that are outside the set E. So let me explain to you what is going on here. Because you assume the function fx over x is going to 0, then and you also know that the set E has size at least A minus FA. So you can assume that E is about the same size as A eventually, right? So E is approximately A. But you also know that because A is a disjoint union of E and F, and E has size at least A minus FA. So F must have size at most FA. But because A and E are almost the same size, we can say that, okay, the size of F is bounded by FE. So the reason why we need this inequality is that we are going to apply the F disjoint democracy on them. Because F and E are disjoint, and F is bounded by FE. So we can apply F disjoint democracy on the two sets. Okay. So let's go over these inequalities. The first one here is simply convexity. Right? You pick beta to be the largest coefficient in F. So of course, you have this inequality by convexity. The second inequality here is by UCC, because if you change the size from epsilon E to 1, it doesn't change the norm much if you have a quasi-greedy basis. The next one here, I'm not sure. I think I should zoom it in a bit so that you can see here. The next one here says that I replace beta by alpha because alpha is greater than beta, right? And also I apply the F disjoint democracy on the function F to transform to go from F to E. To go from F to E here. Right? The next inequality is simply UCC. I only insert the scalars En star X here. And the last one is TQG. This one is TQG, truncation quasi-greedy, that I showed you earlier, because E is a greedy set of X. So now we already bound PFX by X, and that's what we want, and we can bound PEX by X as well. Okay, so here are some of the references that that I use, and I hope that by the end of this talk, you already we have a good discussion of thresholding greedy algorithm, almost greedy basis, and we also see the problem of relaxing optimality for to introduce the notion of F greedy type basis, and we also have a flavor of the proof of unexpected equivalence between F greedy and greedy. So thank you very much for attention.
Oh, thank you for very nice talk. Are there any questions or comments?
May I make a little comment?
Yes,
Sure,
please.
go ahead.
I think this direction is very natural and very interesting results.
Thank you.
But the comment what I want to make is that this setting is very closely connected with the setting which we call Lebesgue type inequalities. And there are papers like, for instance, my paper joined with Anna Comment from 2004, and there are a lot of papers by Gustavo Garrigues and Eugenia Hernandez and some other people. So these things are very closely connected. For instance, that result about multivariate Haar system, what you mentioned, it is contained in those results. So that it's not a surprise, but anyway, this is what, and that setting I think also is very, very natural. We did not look for characterization of this kind of properties like you study, but upper bounds and some theorems about necessity of those conditions, all this stuff is basically is there. But sometimes under extra assumption that the basis is unconditional or the basis is quasi greedy, something like that. But anyway, I think if you did not look yet at those papers, have a look and it will be interesting for you.
Oh, thank you very much. Yeah.
Thank you. Any others? Okay, if not, thank you so much again for a very nice talk.
Thank you.
Okay, so let me stop.